Apollo was a sprint, 12 days for the longest mission, 8 for the shortest. Get there, plant a flag, collect rocks, come home before anything catastrophic had time to accumulate. The engineers who designed the Apollo hardware understood that they were building for a sprint, and they optimized accordingly, accepting risk profiles that a longer mission duration would have made unacceptable, pushing hardware and human physiology to margins that worked precisely because
Artemis
the exposure
II
window
is about
was
to
short
send
enough
humans
that the
into
margins
situations
held.
no one has
Artemis
ever
II
experienced
is not
before.
A sprint. It is a 10-day
For more than 50
endurance
years,
test
no astronaut
conducted
traveled
inside
beyond
a
low
pressurized
Earth orbit.
aluminum capsule
Since
16.5 feet
1972,
wide,
every crewed
orbiting
mission
the moon
stayed
at
inside
velocities
Earth's
that make
protective
emergency
magnetic
return
field.
impossible.
Generations
In a
grew up
radiation
with space
environment that the
stations,
sun
shuttle
is
launches, and
currently
robotic
making
probes,
significantly
but
more
no
hostile
human
than
went
it was
back into
during
deep
any
space.
Apollo mission, with
Now that
4 human
changes.
beings whose bodies
Artemis
were
II is not a
evolved over
continuation
millions
of
years
Apollo.
for an environment
It is not
that
a
stops
sequel mission
existing
repeating
the moment
history.
the hatch closes
It
and the
represents a
launch
different
sequence
technological
initiates.
era,
The
a
public
different
narrative
philosophy of
surrounding
exploration,
Artemis II
and a
is
completely
narrative
new
of
approach
triumph,
to
of
surviving
return,
beyond
of
Earth.
humanity reclaiming
Let's start
its
with something
place in the
simple.
cosmos. This
Space
script is
inside
not
the
that
spacecraft.
narrative. This is the
The
other
Apollo
document,
command
the one that
module gave 3
describes what the
astronauts
4
about
people
210
inside that
cubic
capsule
feet of
are
habitable
actually going to
volume.
experience
That
in
is
their
roughly the
bodies,
size
in
of a
their
large
cells,
closet.
in the biological
3 people
reality
lived
of
in
what
that
it means
confined
to be
space
a
for up
living
to 2
organism
weeks.
in an environment
Orion,
specifically
the spacecraft
structured to
flying
kill
Artemis
living
II,
organisms.
provides
This
about
is the human
330
toll.
cubic
The
feet
first
for
thing
4
that happens to the
astronauts.
human body
That is
during the
nearly
Artemis II
60%
launch
more
sequence
room.
is not dramatic
It is still
in the way that
compact
the
and still
external
demanding,
spectacle is
but
dramatic. From outside the spacecraft, the ignition of the Space Launch System's 4 RS-25 engines and the simultaneous ignition of the twin solid rocket boosters is a visual and acoustic event of extraordinary scale. 5.5 million pounds of thrust, converting liquid hydrogen and liquid oxygen and solid propellant into controlled violence at a rate that produces 15% more thrust than the Saturn V. From inside the Orion crew module, the experience is different. The vibration begins before the vehicle clears the tower, not the clean mechanical vibration of a precisely balanced system, but the broadband acoustic vibration of a structure being shaken by combustion at frequencies that span the entire range of human auditory perception and extend well below it into the infrasound range that the body feels rather than hears. The crew's vision blurs, not from acceleration forces yet, but from the vibration frequency coupling with the resonant frequency of the human eyeball, a phenomenon called visual disturbance that mission planners account for and that training prepares the crew for, but that preparation does not eliminate. The crew cannot read their instruments clearly during the peak vibration phase of ascent. They are monitoring by memory and by feel, while the vehicle shakes at frequencies that make precision visual tasks impossible. Then the acceleration builds. The solid rocket boosters are providing more than 75% of the initial thrust, and they are not throttleable. They burn at their design thrust level until they are exhausted, which takes approximately 2 minutes, and during those 2 minutes, the crew experiences a sustained acceleration load that peaks at approximately 3.5 g. 3.5 g means that every kilogram of body mass is experiencing 3.5 kilograms of effective gravitational force pressing it into the seat. A person weighing 80 kilograms effectively weighs 280 kilograms during peak acceleration. The cardiovascular system
Also more powerful than the one that carried Apollo crews.
And blood pressure to
While
maintain
Saturn V
adequate
defined an era,
perfusion to the
the
brain
Space Launch
against
System
the
produces
increased
even greater
effective
thrust at
gravity,
liftoff.
draining blood toward
Both
the lower
rockets
body.
are
The
expendable
respiratory
heavy
muscles
lift
work
systems,
harder
but
against the
Orion
increased
sitting on
weight
top
of the
represents a
chest wall. The
generational
spine
shift.
compresses
Apollo
under the increased
spacecraft
axial
generated
load. None of
electricity
this
using
is
fuel
acutely
cells.
dangerous for a healthy,
Once
trained
reactants were
astronaut
consumed,
in a properly
power
fitted
margins
launch
narrowed.
suit in the correct body
Orion
position.
unfolds
All of
large
it is a
solar arrays
significant
once in
physiological
space,
stress
generating
event that the
continuous
body
electrical
registers
power
and
as long as
responds to
sunlight
at
is
the
available.
cellular level,
The
initiating
regenerative
stress
capability
response
allows for
cascades
stronger
that will take
redundancy
hours to
and greater
resolve
flexibility
after the
in
acceleration
spacecraft
phase
operations.
ends. The crew
Another
of Artemis
difference is
II will
international
spend the first
collaboration.
several hours of their mission
Apollo
with
was
their
a
bodies
national
recovering
effort.
from the physiological
Artemis is
shock
global.
of getting off the ground.
The Orion
when the
service
solid
module
rocket
was built in
boosters
Europe.
separate 40
A
kilometers
Canadian
above
astronaut
the
is
Earth,
part of
and
the
vehicle
Artemis II
continues
crew.
on RS-25
Future lunar
engine
missions
thrust
will
alone.
include
The
hardware
acceleration
contributions from
profile
multiple
changes.
international
The remaining
partners.
thrust is lower,
Deep
smoother,
space
more
exploration
controlled,
is no
but the
longer a single
environment
nation's
outside
project.
the spacecraft is changing
Inside
in a way
Orion,
that the
the
instruments are
computational
registering
difference is
and the crew
dramatic.
understands but
Apollo's
cannot
guidance
feel
computer
directly.
operated
They are
with about
climbing through
72
the atmosphere,
kilobytes of
the
memory.
atmospheric shielding
Today,
that has protected
even
the
simple
crew
devices
from space
exceed that
radiation
capacity
since
by
birth.
millions
The
of
column
times.
of air above their heads
Orion's
that
flight
absorbs
computers
the
are
majority
tens of
of the
thousands of
cosmic ray
times more
flux and the
capable than
solar
Apollo
particle
systems.
radiation before
The
it
cockpit
reaches
is fully
the surface
digital,
is thinning
using
at
advanced
100
displays and
kilometers. The
software-driven
Kármán line, the
interfaces
conventional
rather than
boundary of
rows of
space, the
analog
atmospheric
switches.
shielding is
Apollo
effectively
astronauts
zero.
depended
The crew
heavily
is
on
now
mission control
exposed
for
to the full
calculations
flux
and trajectory
of the space
updates.
radiation environment.
Orion is
They have
designed to
crossed from
function
the
with far
biosphere
greater
into
autonomy.
a region where the physical
Artemis
forces that
II
shaped
astronauts are
biological
actively
evolution
testing
for
manual
4
piloting
billion
modes in
years
deep
do not
space,
apply.
preparing
The
for a
suits
future where
provide some
communication
protection.
delays
The
make
spacecraft
real-time
structure
assistance from
provides
Earth
some
impractical.
protection. Neither provides
Communication
the protection
itself
that
has
a
changed.
kilometer of atmosphere
Apollo
provided
relied
from the
entirely
moment they
on
were
radio
born
transmission.
until the moment they crossed the
Bandwidth was
Kármán
limited.
line. The radiation
Images took
exposure
significant
begins
time to
accumulating
send.
from that moment,
Orion
and the
carries
environment
laser
into
communication
which they are
technology
flying
capable
is
of
currently
transmitting
more
high volumes of
radioactive
data
than any
at far
environment
greater
that any
speeds.
Apollo crew
High-resolution
encountered.
imagery
The sun
from deep
operates
space
on
can
an
be delivered
approximately
far more
11-year
efficiently than ever
cycle of
before.
magnetic activity.
The view
At
of the
solar
moon will
maximum,
also be
the
different.
frequency and intensity
Apollo
of
crews
solar
flew relatively
energetic
low
particle
over the
events,
lunar
coronal
surface,
mass
seeing
ejections,
terrain in
solar
close
proton
detail.
events, the various
Artemis
categories
II
of
follows
solar
a trajectory
activity
that
produce
allows astronauts to view the
significant
entire
increases in the
lunar
particle
disk.
radiation environment of the inner solar system reach their peak for the cycle. The Apollo missions flew during a period of solar activity that included one significant solar proton event in August 1972 that occurred between Apollo 16 and Apollo 17. The timing was fortunate in a way that the astronauts themselves have acknowledged. Had that event occurred while a crew was in transit, the radiation dose received in the unshielded translunar environment would have been severe and potentially fatal. The Artemis II mission is flying during a solar maximum period. The statistical probability that a significant solar energetic particle event will occur within the 10-day mission window is meaningfully higher than it was during any individual Apollo mission. Mission planning accounts for this through space weather monitoring and through the storm shelter provisions within the Orion crew module. The accounting does not eliminate the risk. It manages it to an acceptable level, and acceptable in the context of human spaceflight risk analysis means something different from acceptable in most other engineering domains. What happens to a human cell when a cosmic ray passes through it is not a metaphor. It is a physical event with physical consequences that the cell's repair mechanisms may or may not be adequate to address. A high-energy proton from a galactic cosmic ray or a solar energetic particle event travels through the spacecraft hull and through the human body at a significant fraction of the speed of light. As it passes through biological tissue, it ionizes the molecules in its path, stripping electrons from atoms and producing reactive chemical species that damage the molecular
response
structures
and radiation
at contact.
dosage in
When
far
the
more
path of the
detail than
particle
during
passes
Apollo.
through a DNA
The
molecule,
data collected
the
will shape
ionization
mission
events
planning for
can
future
break the
journeys,
chemical
including
bonds
Mars.
holding the DNA
For the
strand
first time in
together,
history,
producing
4
strand
humans
breaks
are
that the
traveling in
cell's
deep
repair
space
mechanisms
simultaneously.
must identify and
Apollo
correct.
missions
Single
carried
strand
3 beyond
breaks
Earth
are corrected
orbit.
efficiently
Artemis
in most
II
cases.
expands
Double
that number,
strand breaks,
marking
where
the
both
largest human
strands of the
presence
DNA
ever
double
this far
helix
from
are
home.
broken in close
And then there is the
proximity, are
silence.
more challenging for
When
the repair
Orion passes
machinery
behind the
and more
moon,
likely to
communication
result
with
in
Earth
either
will
cell
stop.
death or, in
No
the worst
signal
case
can
scenario,
penetrate the lunar
mutations
mass.
that alter
For a
the
period of
cell's
time, the
behavior
crew
in
will be
ways that may
completely
not
cut
become
off.
clinically apparent
Apollo
for years
astronauts
or
experienced
decades.
that
The
same
crew of
silence
Artemis
decades
II
ago.
will spend the first
That part
several
has not
hours of their
changed.
mission with their bodies
moon still
recovering
blocks
from the
radio waves.
physiological shock of getting
Space
off
is
the
still
ground.
vast and
When the
quiet.
solid rocket boosters
But everything
separate 40
surrounding that
kilometers
silence
above
is
the
new.
Earth and the vehicle
Apollo
continues
proved
on
that humans could reach
RS-25
the moon.
engine thrust alone.
Artemis
the
is testing the
acceleration
systems
profile
that will allow
changes.
humans
The
to
remaining
build a
thrust is
sustained
lower,
presence beyond
smoother,
Earth.
more controlled.
Life
But the
support,
environment
navigation,
outside the
communication,
spacecraft
radiation
is changing
monitoring,
in a way that the
re-entry
instruments
systems,
are
all of it is
registering,
being
and the crew
validated not just
understands
for a
but cannot
flyby,
feel
but
directly.
for
They're
long-duration
climbing
missions
through
in the
atmosphere.
future.
The atmospheric
This mission is not
shielding
about
that
repeating
has protected
history.
the crew from space
It is about
radiation
extending
since
it.
birth. The
Right
column
now,
of air
4
above their heads
astronauts are
that
farther
absorbs
from
the
Earth than
majority
anyone
of the
has been
cosmic
in more than
ray
half a
flux and the
century.
solar particle
They are
radiation
flying in a
before it
spacecraft
reaches
more
the
advanced
surface
than
is
anything
thinning
Apollo
at
engineers
100
could have
kilometers.
imagined.
The Kármán line,
Yet at
the
its core,
conventional
the
boundary
challenge
of
remains
space,
the same.
atmospheric shielding
sealed
is effectively
capsule.
zero. The
Air
crew
to
is
breathe,
now exposed
water
to
to
the full
drink,
flux of the space
protection from heat,
radiation environment.
radiation, and
They have
vacuum,
crossed from the
and a safe
biosphere
return
into a
home.
region where the physical
The silence
forces
behind
that
the moon
shaped
remains
biological
unchanged.
evolution for 4
Everything
billion
else has
years
moved forward.
do not apply. The
Have you ever
suits
wondered what
provide
it would
some
be like to
protection.
explore
The
deep
spacecraft
space?
structure provides some
For over
protection.
50 years,
Neither
humans have
provides the
stayed within
protection
low
that a
Earth orbit.
kilometer of atmosphere
The last
provided
crewed
from
mission
the moment
beyond
they
that
were
was in
born until the moment
1972.
they
The seal takes 4 seconds to breach completely. In the first second, the pressure differential between the suit interior and the lunar vacuum outside begins forcing gas gas through the compromised seam at a rate the suit's emergency systems cannot compensate for. In the second second, the atmospheric pressure inside the suit drops below the Armstrong limit, the threshold at which the ambient pressure is so low that liquid water at human body temperature spontaneously transitions to vapor. In the third second, that transition begins occurring not in a glass of water, not in a laboratory apparatus, but in the moisture lining your lungs, in the fluid surrounding your joints, in the saliva in your mouth, in the blood moving through the capillaries closest to your skin surface. In the fourth second, you are still conscious. You can still feel everything. The Hollywood version of vacuum exposure, the dramatic, explosive decompression that ruptures the body from outside in, is wrong in almost every specific detail. You do not explode. You do not freeze instantly. You do not lose consciousness in the first moment. What happens is quieter and more methodical and considerably more thorough. The vacuum does not attack you. It simply removes the pressure that was keeping your body's chemistry in its operational state, and your body begins, with complete physical indifference, to come apart from the inside. The Armstrong limit sits at approximately 6.3 kilopascals of atmospheric pressure. At sea level on Earth, the pressure is 101.3 kilopascals, enough to keep water liquid at temperatures up to 100 degrees Celsius. As pressure decreases, the boiling point of water decreases with it. At the Armstrong limit, water boils at 37 degrees Celsius, which is human body temperature. This means that at pressures at or below the Armstrong limit, every water-based fluid in the human body is at or above its boiling point. The process by which these fluids transition to gas within body tissues is called ebullition. It begins in the tissues with the lowest local pressure, typically the soft tissues of the mouth and throat, and progresses inward. The gases expanding within the subcutaneous tissue cause visible swelling as the skin distends outward to accommodate the increasing volume. An unprotected human being exposed to lunar vacuum would swell to approximately twice their normal body volume within seconds, not because of external pressure acting on the body, but because of internal gas expansion acting from within. The skin does not rupture under this pressure in most cases. It stretches. The soft tissues beneath it expand into the spaces created by that stretching. The process is systemic, progressive, and in the absence of immediate repressurization, irreversible. The heart continues beating for a period after the onset of ebullition because cardiac muscle does not require the same conditions as the surrounding tissue to maintain its electrical activity. The circulatory system continues moving fluid, or what was fluid, through the vessels. The brain continues attempting to process sensory input and generate responses. Consciousness persists for approximately 15 seconds. The experience of those 15 seconds has never been fully documented. The closest analogy in the medical literature comes from altitude chamber accidents, in which test subjects were briefly exposed to near vacuum conditions before emergency repressurization. They reported afterward the sensation of moisture evaporating from the surface of their tongues, and then nothing until they woke up with repressurization underway. The moon's surface pressure is not near vacuum. It is as close to perfect vacuum as any natural environment accessible to human beings. There is no afterward without a functioning suit. The suit is everything on the moon, not a uniform, not a piece of equipment in the conventional sense, but the totality of the survivable environment for the human body inside it. The Artemis generation extravehicular mobility unit that NASA has developed for lunar surface operations is an engineering achievement of genuine complexity. A portable life support system, pressure vessel, thermal regulation apparatus, radiation attenuator, and communication platform integrated into a wearable assembly that must maintain its integrity across a surface environment specifically hostile to every one of those functions simultaneously. The lunar surface presents mechanical challenges to suit integrity that have no equivalent in low Earth orbit operations. The primary mechanical threat is not what you might expect. It is not temperature. It is not radiation. It is dust. Specifically, it is the dust that covers every exposed surface of the moon to a depth that varies from centimeters to meters, dust that the Apollo astronauts discovered within hours of their first surface excursions was unlike any particulate material encountered on Earth, and that subsequent analysis has confirmed is among the most mechanically aggressive substances that human engineering has ever been required to contend with. Lunar regolith is the term used to describe the layer of fragmented material covering the moon's solid bedrock surface. On Earth, regolith is produced by a combination of physical weathering, chemical weathering, and biological activity. Wind and water
water round the edges of particles. Chemical reactions alter their surface composition. Biological organisms break down material and produce new compounds. The net effect of these processes over geological timescales is sediment with rounded, relatively smooth particle morphology, material that compresses and flows, and whose edges, while not harmless, are not acutely damaging to soft biological tissue. The Moon has none of these processes. There is no wind. There is no liquid water. There is no biology. The regolith on the lunar surface has been produced over 4.5 billion years by a single dominant process: impact. Meteorites of every size, from microscopic to continental, have been striking the lunar surface continuously since its formation, shattering the existing rock into progressively smaller fragments, fusing those fragments into glass beads through the intense heat of impact events, and then shattering the glass beads into fragments again in subsequent impacts. The result is a particulate material whose individual grains range in size from submicron to millimeter scale, and whose morphology is the direct product of fracture mechanics, operating without any of the erosional rounding processes that terrestrial sediment experiences. Lunar dust particles are angular. They are jagged. They have sharp edges and concave surfaces and protrusions that interlock with other particles and with the surfaces they contact. Under an electron microscope, a single grain of lunar regolith looks like a fragment of broken glass whose edges were never ground down, because they were not, because nothing on the Moon grinds edges down. Every fragment is exactly as sharp as the fracture that produced it. When Apollo astronauts returned to the lunar module after surface excursions, they noticed something immediately and consistently across all 6 landing missions. The dust that had accumulated on their suits smelled not like rock, not like soil, not like anything terrestrial. They described it as gunpowder, a sharp, acrid, distinctive chemical smell that was immediately on entering the pressurized module, and that faded over the following hours as the reactive surface chemistry of the dust particles interacted with the cabin atmosphere and was neutralized. The smell was not a trivial observation. The reactive surface chemistry that produced it was the same chemistry that makes lunar dust biologically dangerous in ways that go beyond its mechanical sharpness. In the lunar environment, the absence of atmosphere means that the surface of every dust particle is continuously bombarded by solar wind ions and ultraviolet radiation, processes that create unsatisfied chemical bonds on the particle surfaces, dangling reactive sites that normally would be quickly saturated by interaction with atmospheric gases on Earth, but that persist on the Moon because there is no atmosphere to saturate them. These reactive surfaces are what produce the gunpowder smell when the dust contacts the moist atmosphere of the lunar module. They are also what makes the dust chemically aggressive to biological tissue. When lunar dust particles are inhaled, which is difficult to prevent given the particle size range and the static charge the dust accumulates from solar wind bombardment, they do not behave like terrestrial dust in the respiratory system. The mechanical sharpness of the particles damages the epithelial lining of the airways in a manner that researchers have compared to asbestos exposure, not identical in mechanism, but similar in outcome. The particles do not dissolve, they do not break down, they embed in tissue and remain, continuing to damage surrounding cells through both mechanical abrasion and chemical reactivity. The condition that would result from chronic exposure to lunar dust has been termed lunar silicosis in the research literature, by analogy with the terrestrial occupational disease caused by crystalline silica inhalation. The Apollo astronauts experienced limited exposure during short surface excursions. The Artemis astronauts, whose mission architecture involves extended surface operations, base construction, and repeated ingress and exit cycles that each introduce fresh dust into the habitat environment, will face a dust management challenge that the mission planning documentation acknowledges as one of the most significant unresolved engineering problems of the entire program. The dust that covers the Moon is not sand. It is a biological weapon produced by 4.5 billion years of unmitigated violence. The Moon has no global magnetic field. This single fact, which receives considerably less attention in public discussions of lunar exploration than it deserves, is the root cause of the radiation environment that represents the most insidious and least immediately visible threat to human health on the lunar surface. On Earth, the magnetosphere deflects the majority of the charged particle radiation produced by the Sun and the galactic cosmic ray flux that permeates
Here is the sound, a human heartbeat, 72 beats per minute. The sound of a body at rest, a body in a controlled environment, a body surrounded by everything it needs to continue functioning. Oxygen at the right concentration, temperature within a narrow survivable band, atmospheric pressure calibrated to keep blood from boiling in the veins, radiation levels low enough that cellular DNA can repair itself faster than it accumulates damage. A heartbeat at 72 beats per minute is the sound of a human being in an environment built for human beings. Now imagine that heartbeat 450,000 kilometers from the nearest hospital, 450,000 kilometers from the nearest breathable atmosphere that exists outside a machine, 450,000 kilometers from any possibility of evacuation, resupply, or rescue. The heartbeat does not change, 72 beats per minute. The body does not know how far it is from help. The engineering keeping it alive does. And the gap between what the human body requires to maintain that rhythm and what the hardware surrounding it can reliably provide across 10 days in the most hostile environment our species has ever deliberately entered is the story that the press releases and the launch day celebrations do not tell. This is not a celebration of Artemis II. This is an audit of it, a technical examination of what it actually means to keep 4 human beings alive between the Earth and the Moon, what the engineering specifications require, where the margins are thin, and what happens in the scenarios that nobody at a press conference wants to be asked about. The Orion spacecraft that will carry the Artemis II crew is the most sophisticated human-rated vehicle ever built for deep space operations. That statement is accurate, and it is also, if you understand what it means, not entirely reassuring. Sophisticated does not mean simple. It does not mean robust in the way that simple systems are robust. It means complex. It means interdependent. It means that the number of components whose correct functioning is required to maintain the crew's survival is very large, and that the interactions between those components create failure modes that no single engineer or team of engineers can fully map in advance. The Environmental Control and Life Support System, known in NASA's technical documentation as ECLSS, is the subsystem responsible for the most fundamental requirements of crew survival: oxygen generation and supply, carbon dioxide removal, atmospheric pressure regulation, temperature and humidity control, water recovery and management. These are not optional systems with acceptable degraded modes. They are binary in the most literal sense. They work or the crew dies. Not eventually, not after a period of discomfort, within hours in the case of atmospheric management failures, within minutes in the worst-case scenarios involving rapid depressurization. The ECLSS on Orion has been designed with redundancy at every critical junction, backup systems for the backup systems, sensors monitoring sensors, automated fault detection triggering automated responses before any human crew member has time to register that something has gone wrong. The redundancy architecture is genuine, and it is impressive, and it reflects decades of hard lessons learned from every crewed spaceflight program in history. And the thing that the redundancy architecture cannot eliminate, the vulnerability that engineering cannot fully design away, is what systems engineers call redundancy fatigue. Redundancy fatigue is not a failure of a single component. It is a systemic condition that develops when backup systems are called upon to compensate for primary system degradations over extended periods of operation. In a 10-day mission profile, the ECLSS and its associated subsystems will cycle through their operational parameters thousands of times. Each cycle introduces the possibility of incremental wear. Each incremental wear event is individually negligible and collectively significant. The primary carbon dioxide removal system, which scrubs CO2 from the cabin atmosphere before it accumulates to toxic concentrations, operates on a molecular sieve bed that has a finite adsorption capacity before it requires regeneration. The regeneration cycle works in nominal conditions, but molecular sieve performance is sensitive to humidity levels, and humidity levels in a sealed cabin occupied by 4 metabolically active human beings over 10 days drift in ways that are difficult to fully predict from ground testing. If the primary scrubber's efficiency degrades below its design threshold at day 7 of a 10-day mission, the backup
backup system activates. The backup system was designed for this scenario. It was tested for this scenario, but the backup system was not designed to operate continuously for 3 days, while also compensating for any secondary anomalies that may have developed in adjacent subsystems during the same period that caused the primary to degrade. The backup exists for the failure. The backup's own vulnerability exists for the failure of the backup. And at day 7, 450,000 kilometers from the nearest replacement part, the margin between the second backup activating and the third backup not existing is a number that the mission risk analysts know precisely and that does not appear in any public document. The avionics suite governing Orion's navigation, guidance, and control systems faces a different category of challenge rooted in the thermal environment of deep space operations. In low Earth orbit, spacecraft pass through alternating periods of solar illumination and orbital shadow approximately every 90 minutes, creating a thermal cycling regime that hardware is designed and tested to withstand. In the translunar trajectory of Artemis II, the thermal environment is different in ways that matter to the longevity of electronic components. The spacecraft will experience extended periods of direct solar exposure without the cyclical relief of orbital shadow, followed by extended periods of exposure to the deep cold of space, where the sun is blocked by the moon's disk. The avionics suite, the processors and memory systems and sensor interfaces and communication electronics that collectively constitute the spacecraft's nervous system must maintain operational integrity across a thermal range that is wider and less predictable than the low Earth orbit environment for which the majority of the heritage components were originally qualified. Thermal stress on electronic components does not produce sudden catastrophic failures. In most cases, it produces gradual parameter drift, resistance values shifting, capacitor characteristics changing, timing tolerances narrowing, until a component that is technically functional is no longer functional within the precision its role in the system requires. A navigation processor whose clock timing has drifted by a fraction outside its tolerance does not stop working. It starts producing answers that are almost correct, and in a guidance system calculating a translunar trajectory, almost correct is a category of failure that can be more dangerous than no answer at all. The radiation environment of the translunar trajectory represents the most significant and least controllable physical hazard the Artemis II crew will face. Within the Van Allen radiation belts that the spacecraft must traverse during its departure from Earth orbit, the crew will be exposed to trapped high-energy particles at intensities that exceed what is experienced on the International Space Station in low Earth orbit by significant factors. Beyond the belts, in the translunar space between the Earth and the Moon, the primary radiation sources are galactic cosmic rays and solar energetic particle events. Galactic cosmic rays are a constant background that the Orion crew module's aluminum structure and the water and equipment mass of the spacecraft's interior partially attenuates but cannot eliminate. Solar energetic particle events are not constant. They are episodic and partially predictable. When the Sun produces a significant coronal mass ejection directed toward the Earth-Moon system, the proton flux reaching an unshielded spacecraft can rise to levels that would exceed the career radiation exposure limits for NASA astronauts in a matter of hours. The Artemis II mission profile accounts for this risk. The crew has a designated shelter location within the Orion crew module, where the surrounding mass provides the maximum available shielding. The space weather monitoring infrastructure that provides advance warning of significant solar events will be active throughout the mission. The forecast models have improved significantly in recent years, and the probability that the 10-day mission window will overlap with a significant directed solar energetic particle event is calculated to be low. Low is not zero. The margin between a manageable radiation exposure and one that has immediate acute effects on crew health is a function of event magnitude, duration, and the crew's physical position within the spacecraft at the time of peak flux. All three of these variables are outside the crew's control. Now, stop. Let the technical language go for a moment. Let the specifications and the redundancy architectures and the thermal cycling parameters recede, and consider instead what it actually feels like to be a human being in that spacecraft at the moment described in the mission timeline as Day 6, the lunar flyby. The moment when the crew passes around the far side of the moon and communications with Earth are cut completely. No signal, no voice, no data link, no confirmation that the trajectory is nominal, that the systems are performing within